The Department of Earth and Planetary Sciences was formed in 1968 as the result of a merger between the Geology and Oceanography departments at Johns Hopkins, one of the first departments of Earth and Planetary Science in the country. The department's three major areas of focus right now are the fluid dynamics of planetary systems, the history of the Earth, and the behavior of planets as systems, not just within the solar system, but even outside the solar system, including exoplanets. The concept of change is vital to the research because planets are dynamic systems. Different parts of the planets change over time, and those changes have impacts not only on the particular process that one is concerned with, but potential changes for the whole evolution of the system, including life itself. And we've hired a bunch of people in the last few years who also think in terms of planets as systems.
At Hopkins, we're working to understand both the modern and ancient climate of the planet Mars. In the past, we thought that most of the geological activity on Mars happened in the ancient past, and certainly a lot of it has. Using data from missions like the Curiosity rover, we've been able to show that the modern surface environment is much more dynamic than we had appreciated, and that sediment is moved frequently, both on daily and annual timescales. On Earth, the sedimentary rock record tells us all sorts of things about the history of our own planet, from plate tectonics to the evolution of life. On Mars, we used to think the surface and crust of the planet was dominated by volcanic rocks, but in the past 15 years or so, we've come to appreciate just how common sedimentary rocks are on the surface of Mars as well. In my lab, we've been using analysis of these rocks to help us understand what the ancient Martian past was like, and these rocks really give us a window into the ancient history of Mars, as well as the first billion years of solar system evolution.
So I am really interested in fossils, especially Ediacaran and Cambrian fossils. And I'm interested in periods of change. I'm interested in extinction events and radiation events. So I'm looking at these fossils in the context of environmental changes that are happening at the same time, before or after, and try to link the fossil record with other proxy records. And there are all these interesting environmental changes associated with these big shifts in life. One of the places where I do fieldwork is the Southwest US. About 5 years ago, we discovered some Ediacaran fossils. So Ediacaran fossils are incredibly rare. We discovered a range of shapes, a range of sizes, and so it launched this whole project, and now we're working on the taxonomy of these fossils, the paleo-environmental context of these fossils, and trying to link these fossils with different environmental proxy records.
In the case of deep rocks, which formed in environments that aren't directly observable, there has been sometimes a propensity towards interpretation of their formation and the processes they record as uniform rate and protracted. Work that colleagues of mine and I are doing is starting to suggest that these rocks and processes may include great non-uniformity in rates, such that what they record relates to their more memorable moments rather than their everyday experience. Punctuated equilibria refers to processes of evolution that proceed by rapid changes punctuating periods of relative stasis. Concepts analogous to punctuated equilibrium may be applied to plate tectonics in terms of viewing tectonic processes as drawn-out, long time frame periods of dynamic equilibrium that are punctuated by plate reorganization events and relative tectonic upheaval. The question is then, how much of the rocks and landscapes that we see and interact with are formed as a result of these periods of tectonic upheaval and reorganization, as opposed to the periods of relative steady state typical conditions.
Ecologists have traditionally ignored cities, but they're actually the location where most humans interact with their environment and are dynamic ecosystems in their own right. And understanding the ecology of cities is key to meeting sustainability goals. Ecologists have a long history of doing ecosystem level studies where we conceptualize systems as a whole. And by bringing this approach to cities, we can better plan cities for both the environment and future inhabitants. My research at Cons is really focused on how global change in general is going to affect plant communities and the resultant ecosystem services they provide. And I apply what I learn and understand from these more natural systems in tallgrass prairies to very managed and constructed communities here in cities. Ultimately, what we're trying to understand is if ecological theory holds up across very managed landscapes.
We're used to thinking about rock chemistry as reflecting the environment, but we're also learning that it may reflect the organisms that live in and modify the environment. So a major change that we're understanding in rock chemistry, and specifically in ocean chemistry in the past, is that rocks record local conditions as well as global conditions. Sometimes we like to look at the rock record and think that we're looking at secular variation in seawater chemistry, but sometimes they're recording local environmental signals. And the thing that's really exciting about that is that knowledge of both local and global processes is really necessary for us to understand how the environment changes and how it responds to things that might stress a system. So one thing that's really great about being at Johns Hopkins University is we're close to Chesapeake Bay. And Chesapeake Bay is an estuary that is economically important, but it's also home to a really large dead zone. Dead zones are places in the ocean where there's no oxygen in the water column. And we really want to understand how these dead zones are going to either expand or contract under future scenarios of warming, because that can affect fish and other things that live in the ocean, as well as ecosystem health.
So you've just seen a snapshot of the research that's going on in this building. It's changing our view of many, many systems, from planets to ecosystems, and we look forward to seeing how that's going to develop in the next decades.